All right, let's just dive right into this. Welcome to This Explainer. Today, we're unpacking the science and real-world application of what is, honestly, an absolute industrial superhero. Now, you might never actually see it, but it cleans the water you drink, speeds up the manufacturing of the paper you use every day, and literally keeps heavy-duty oil drilling operations from collapsing. We're talking about a chemical known as polydadmac, and we're going to break down exactly how this heavy-hitting polymer works its magic.
So here's our roadmap for today. 1. Meet the flocculant hero. 2. The chemistry of coagulation. 3. Polydadmac versus traditional coagulants. 4. Papermaking and oil drilling. And finally, 5. Safety and handling.
Okay, Section 1. Meet the flocculant hero. What exactly is polydadmac?
At first glance, it doesn't look like much, right? It's just this simple, clear to maybe slightly yellow liquid. But commercially, polydadmac is usually supplied as this highly soluble, incredibly viscous liquid concentrate. It usually contains anywhere from 10 to 50% active solids by weight, and it's designed exactly like this so that industrial plants can easily handle it, pump it, and dose it right into massive streams of water.
But to really get why it's such a game changer, we kind of have to define what it is chemically. Polydadmac is a cationic polymer. In everyday terms, that means it's a synthetic, water-soluble molecular chain that carries a permanent positive charge. This charge actually comes from a super dense array of what chemists call pyrrolidinium rings, which are built right into the polymer's backbone. And here's why that matters. Most of the junk suspended in water, like dirt, organic waste, tiny fibers, it all carries a negative charge. So this permanently positive polymer acts like a giant microscopic magnet, just aggressively attracting and binding up all those unwanted particles.
And it's not just the electrical charge doing the work, it's the sheer mind-boggling size of the thing. The molecular weight of these high-performance commercial polymers, like think of the Superfloc C591 series, for example, can easily exceed 1 million Daltons. A million! That massive physical scale is the real secret to their power. They aren't just canceling out charges, they are literally large enough to wrap around and pull massive amounts of debris together.
Moving on to Section 2. The chemistry of coagulation. Let's look at how polydadmac actually does this.
The whole microscopic process really boils down to a super fast two-step mechanism. If you can wrap your head around these two concepts, charge neutralization and particle bridging, you will fundamentally understand how modern water clarification works.
So, Step 1. Charge neutralization. I want you to picture an electrostatic scale. Suspended colloids like silt in river water naturally repel each other because they all have a negative surface charge. They literally bounce off one another and just stay perfectly suspended in the water forever, which creates what we call turbidity or cloudiness. Well, polydadmac swoops in and balances that scale. Its intense positive charges totally cancel out the negative ones. It drops the electrical potential of those particles, which is known as the zeta potential, down to near 0 millivolts. Without that repulsive force pushing them apart, the particles are completely destabilized and can finally start clumping together. Then comes Step 2, particle bridging. This is where that massive molecular weight of over 1 million Daltons really flexes its muscles. Imagine these huge, incredibly long polymer chains practically throwing a physical net over all those newly neutralized particles. Because the polymer is so massive, it grabs onto multiple particles at the exact same time, bridging them together into these really dense, compact clumps called flocs. And because they're all tied together by this flexible chemical chain, these flocs are super shear resistant. They don't just break apart when the water gets agitated, and they settle right out of the liquid incredibly fast. It's brilliant.
Section 3. Polydadmac versus traditional coagulants. You know, we've been treating industrial water for over a century, so how does this synthetic polymer stack up against the old-school chemicals?
It completely comes down to efficiency and cleanliness. For a really long time, the standard go-to was using inorganic metal salts, like aluminum sulfate, commonly known as alum. But look at the difference here. Aluminum salts are super sensitive to the water's pH, they can leave behind unwanted metal contaminants, and worse, they generate an absolutely massive amount of wet, sloppy sludge. Polydadmac, on the other hand, it works flawlessly across a huge pH range, leaves 0 metal residuals, and crucially, it drastically shrinks the volume of sludge you have to deal with.
In fact, the source material explicitly notes that it, quote, generates less sludge volume than inorganic alternatives by producing denser, more compact flocs that dewater more easily. Think about what that means for a municipal water manager processing millions of gallons a day. Less sludge means a massive drop in disposal costs and a significantly lower environmental footprint. It is basically a win-win.
Okay, section 4, papermaking and oil drilling. Because polydadmac absolutely isn't just for municipal drinking water. It's a total workhorse in some of our heaviest, messiest industries.
Take a paper mill. You've got this massive flowing soup of water, wood fibers, and chemical fillers. Polydadmac acts as a powerful retention aid here. It neutralizes the negatively charged anionic trash in the water, capturing all those valuable fine fibers and fillers that would otherwise just wash right down the drain. And because it binds those solids together so effectively, the water drains out of the paper mat way faster on the machine. This accelerated drainage actually lets paper mills crank up their operating speeds by 10 to 20%. That is a huge boost to their bottom line.
So we know it clarifies water, we know it speeds up papermaking, but what about oil drilling? How on earth does a water-soluble polymer survive the extreme high-pressure chaos of a drilling rig?
Out on the rigs, polydadmac is actually deployed as a critical shale stabilizer in water-based drilling fluids. See, when they drill through shale formations, the clay naturally wants to soak up water, swell up, and disperse. If that happens, the wellbore can totally collapse and shut the whole operation down. By pumping in polydadmac, those positive charges instantly neutralize the negative charges on the clay particles. It essentially locks the clay in place, prevents any swelling, keeps the wellbore structurally sound, and stops dangerous, wildly expensive downtime.
Let's look at Section 5, Safety, Spills, and Handling. Because honestly, when you're deploying thousands of gallons of any industrial chemical, you need incredibly strict protocols. And there's a really surprising reality when it comes to managing this specific chemical. On a strictly biological level, polydadmac has very low acute toxicity. In animal studies, its oral LD50 is actually over 5,000 milligrams per kilogram. It's generally safe regarding accidental trace ingestion, which is exactly why it's approved for drinking water treatment in the first place. But please, do not let that fool you into thinking you can just splash it around. On an industrial floor, it presents a massive physical hazard.
If you pull up the safety data sheets, the huge flashing warning is all about spills. Remember, it's a highly viscous liquid polymer. If you spill it, it creates an extreme, ice-like slip and fall hazard. It literally turns a concrete factory floor into a frictionless ice rink. And you can't just hose it down. Throwing water on it just makes it spread out and get even slicker. It requires super careful dilution and specialized absorbent materials to clean up. Plus, handling it mandates strict personal protective equipment. You absolutely need gloves and goggles to prevent skin and eye irritation. Out on the floor, managing its physical properties is just as serious as managing its chemistry.
Which kind of leaves us with a much larger question to chew on. Polydadmac is undeniably incredibly effective. It significantly reduces chemical waste and sludge compared to older methods, but it is still a highly persistent synthetic polymer that doesn't easily biodegrade in the environment. So, as we continue to rely heavily on these brilliant chemical tools to clean our water and power our modern industries, how do we balance their immense necessary efficiency with their long-term environmental footprint? It's a serious challenge, and it's one that the next generation of chemists and engineers is going to have to figure out. Thanks so much for joining me for this explainer, and keep asking the big questions.